Hello and welcome to another episode of Enough with the Science. I'm Joe.
And I am Senan, and boys oh boys, have we got an exotic episode for you this week, Joe.
Exotic indeed.
What images does that word conjure up for you?
Well, somewhere very far away from here. I've seen
like
palm
maybe-
trees, white sand beaches.
I was thinking maybe Pluto or,
Yeah. See, we live in very different worlds. Very different worlds. Quantum physics, that's where we're at.
Well, exotic for me, when I was young and, was partial to the occasional dram, Sunday morning was a good, my state of my matter on a Sunday morning was, exotic was the right word for it.
Exotic, that's as exotic as you want to get.
So yeah, that's the worst segue I've ever done. But anyway, the topic of this
And there is severe competition for that. I'll have you know. There's a few of them in there.
The topic of this week's show is exotic states of matter.
Not exotic states of mind.
Yeah.
Exotic states of matter.
And it's highly likely that this will be a two-parter.
I think it has to be a two-parter because there are a lot of exotic states of matter.
Yeah. And we're going to be slightly dipping our toes into the corrosive acid of quantum physics.
Because here we go. Wave or particle, wave or particle, wave or particle.
That's where all the
Wave or
weirdness.
particle.
Stop waving at the particles.
My brain hurts already.
Right. I suppose if we're going to talk about things being exotic or weird, we first of all need to try and define what's not exotic or weird. What's
I love this. Where is the baseline?
Yeah, where is the baseline? Right. So let's talk about what is normal matter made up of anyway. So it's made of atoms or molecules, and a molecule is just two or more atoms stuck together. Right.
Okay.
But of course, you can dig a little bit deeper than that, and you've got a nucleus in the middle of the atom, which is made up of a mixture of protons and neutrons. Protons have a positive charge. Guess what kind of charge neutrons have?
None.
Yeah, correct. Go to the top of the class. And then somewhere drifting around the outside of that is a bunch of electrons.
Okay.
They, of course, have a negative charge. So
an atom is mostly space.
Huh?
An atom is mostly space.
Well, the distance, the empty space between the nucleus and the electrons is quite large. Yeah. Mm-hmm. And the negative charge typically of the electrons is balanced out by the positive charge of the protons in the nucleus. So you end up with a thing that doesn't really have an electrical charge.
Okay.
Right?
That's what you want in normal matter states.
Pretty much, yeah. And then if you dig even a little bit deeper than that...
Because we should, because we are a science podcast.
Yes. You find that protons and neutrons in the nucleus are actually made up of something called quarks. And they are...
Quark's bar in Star Trek. Quark was the name of the guy who owned the bar in Deep Space Nine, wasn't he? Quark's bar? Am I losing my mind? Maybe.
I'm thinking of, the one Whoopi Goldberg played? That was in a different Star Trek, wasn't it? She was Guinan, was she?
She was Guinan, yeah. I think she was in The Next Generation.
Okay.
Yeah. No, but Deep Space Nine, I think, was Quark's bar.
Yeah, I never saw a lot of Deep Space Nine. Was that the one with Janeway in it?
No.
That was Voyager, was it?
Yeah. We can't even, we have no right to have this podcast. We don't know the difference between our Star Treks.
I know. Anyway, back to the matter in hand. Okay,
quarks.
Quarks are glued together by something called the strong nuclear force, which we mentioned briefly in an earlier podcast talking about fusion.
Now, hold on. So quarks are they're the building blocks of neutrons and protons.
Yeah. Now, there are lots of flavours of quarks. There isn't just one thing called a quark.
Is a proton with one type of flavors or a group of flavors and a neutron is a different type, or are they kind of mixed like they could have any type of quark? Just nod your head. Yes, that's to be checked.
The truth lies somewhere in that explanation.
Yes.
Anyway, we've got something then called force carriers, which are gluons. And they carry the strong nuclear force between the particles to glue them together.
The quarks. They glued quarks together?
Yes, correct.
Okay.
Yeah. So gluons are really originally named because they glue things together.
I like that. I like it when it's simple.
So then we have us humans in our daily experience. There's three kind of states of matter that we are familiar with, right? So solid.
Okay.
You can hit it and it makes a noise when you hit it.
Is that the scientific definition?
Anyway, the atoms of the molecules are locked into fixed positions, locked together. They're held together by a strong bond that locks them into a position. They're still vibrating because anything that has heat is vibrating. Any molecule, any material that has heat, its molecules are vibrating. That's how the heat is expressed, if you like. And some of them are even in crystals where it's like a grid or a regular lattice repeating pattern, that they're in a very defined pattern, and the same pattern repeats throughout the material.
Right.
And lots of materials that we're commonly familiar with are crystals. Obviously, there's ice,
Crystal.
there's salt, there's crystal swing, there is metals. Most metals are crystals. So, in fact, I think all of them are. So, yeah, crystals. But even
I'm just wondering how many people will get that reference to crystal swing.
somebody should look it up.
So somebody should look it up.
Yeah, look up the YouTube videos. It's an education.
Yeah.
Anyway, then we have liquids, right? The particles are still alongside each other, but now they've got a little bit more energy, so they're not locked in place. They're free to slide past each other. So liquids are able to flow because the particles, although they are together, they are able to slide around past each other.
Right.
And then if you keep adding a bit more energy, now you've got a gas, because you've given the particles enough energy that they can break away from each other. They're not stuck together anymore. And if you put them into a container, they will literally expand to fill the full container.
Okay.
And they're now moving much faster, and their motion is more random. It's in all directions.
Can I just throw something in to confuse things completely?
Yeah, why not?
Because, okay, you were saying that some things are liquids, some things are solids, some things are crystal. What are the other types of solids? They're not crystal then.
Amorphous.
Amorphous solids.
Yeah.
So glass is an amorphous solid.
Correct.
Because it flows slowly. So that,
Yeah, I did not know that.
Yeah, but like if you look at medieval churches, apparently the glass at the top of the frame or top of the pane is much thinner than the glass at the bottom of the frame over a long period of time. So that means that technically,
I'm getting back to the Sunday morning exotic state. When I used to be a mass going good Catholic, I mean, I can remember seeing the stained glass moving, and it wasn't all that slow.
No, well, that's unfortunately we can't help you with that in this podcast. So, but then technically, because crystal is glass, then crystal is not crystal; it's amorphous.
You mean what we call crystal? So, like Waterford crystal or Cavan crystal, decorative glass that has been put in patterns is not actually a crystal. Yeah. So, just everything you know is a lie, Joe.
There you go. That's it. Right.
So,
continue.
And the basic thing that's going on here that determines what state something is in, whether it's solid, liquid, or gas, is a tug of war between the bonding forces that stick the atoms together and the amount of energy, i.e., heat, that has been given into that substance.
Right.
So it's which side of that battle wins depends whether it's a gas or a solid or a liquid. Now we come to what's known as the fourth state of matter, something that we humans rarely experience in our daily lives, but is actually the most common visible, by far the most common state of matter visible in the universe.
Right.
And that's plasma.
You've intrigued me. I don't know about anybody else, but I'm intrigued now.
So at night time, you go out in the garden on a clear night and you look up at the sky. Every single piece of light you can see is plasma.
Right.
And you look at the sun on a sunny day, you're looking at a big ball of plasma. So all the stars, all the galaxies, which are just bunches of stars, are all plasma. What happens? Well, you keep adding energy. So you've already added enough energy to turn your substance into a gas. You now keep adding energy. And what happens is you give the electrons enough energy that they can break away from the electromagnetic force that's holding them to the protons. So before they become a plasma, the the difference in charge between the negative charge of the electrons, positive charge of the plasma of the protons, is enough to hold those electrons in orbit around the nucleus. You give them enough energy now, and they will break away. So you've now got this soup of free electrons flying around and free nuclei without their electrons, which are now being called ions, also flying around. So you've now got charged particles. Before, the atoms didn't really, or the molecules didn't really have a charge because the electrons balanced out the protons. Right. Now you've got two different bunches of charges floating around in this soup. So now it can carry electricity where it couldn't before. And now you can control it with a magnetic field. So, say like in our experimental fusion reactors, we've got fusion plasma, and we're using very strong magnetic fields around the outside to steer that plasma around in a circle.
Okay.
And how much heat is involved? Neon science. That's actually plasma. The neon gas has been turned into a plasma. And there's at least 10,000 degrees centigrade, maybe even as much as 15,000
A neon sign.
in the neon sign.
And if that doesn't scare you, because it certainly scares me.
But the thing is, right, it should melt the glass. I mean, 10,000 degrees Celsius is far more than you need to melt glass. But it doesn't, because it's just the electrons that are at that temperature. And in terms of the mass, there's far more mass in the nuclei, in the protons and the neutrons, than there is in the electrons. So the percentage of the material that's at that high temperature is tiny.
Right.
So it's not enough to actually melt the glass, even though the individual temperatures of the electrons would be that temperature. Like lightning. Momentarily, a lightning bolt heats air up to 30,000 degrees, creates a plasma channel. And that allows the electricity to flow, because now you've got a charged substance which can carry electricity. And it also glows because you might think back to our long ago episode on the electromagnetic spectrum, and we discovered that when charged particles accelerate or decelerate or change direction, they generate electromagnetic radiation. And light, of course, is one particular type. So,
of course, I remember that. Of course.
So the light in a lightning bolt is the electromagnetic radiation generated by those charged particles accelerating in the lightning bolt.
Right.
So yeah, and it's the same in the neon. The light is created by the charged particles accelerating in the neon sign.
So plasma is the fourth state of matter.
Yeah.
And so technically, if it gets any hotter than that, then it's energy, not matter anymore. Is that?
Well, there is something that we probably won't get to until next week, is something called a quark gluon plasma, which happens at really extreme temperatures and probably only occurred for a split second just after the Big Bang.
Wow. Leave that till next week. Leave it till next week.
So yeah, the interesting thing about heat is you can just keep, if you've a source of energy, you can just keep piling on more and more and more heat.
Unlike being cold. When you go down the other,
there is a limit.
The limit to coldness.
You can get, and we're actually coming to that now, because what happens? It's a very excellent segue, Joe.
hours I've been working on that.
We're now going to talk about what happens when you cool things down rather than heating them up.
I think that's a good idea, because we're getting a little extreme here.
We are. I'm starting to sweat just at the thought of it.
Yeah.
So superconductivity is something that emerges out of making metal wires very cold. Before we talk about superconductivity, what is normal?
Too late.
What is normal conductivity? Yeah, well, okay, I probably. How do you introduce it without mentioning it? Anyway, normal conductivity. You have a wire. It's at room temperature. You can hold it. It's not terribly cold, and you connect a battery to it, and you connect a bulb at the other end, and hey, current flows through. The light comes on. It looks like the electricity is flowing through that wire, no problem. The reality is some of the energy is being lost in the wire. The wire has a property called resistance, and a small amount of the energy that's flowing through the wire is being lost as heat. And how that's happening is, as the electrons rush through the wire to carry the electricity, they're bumping into the atoms that the wire is made of. And every one of those collisions wastes a little bit of heat from the friction of the collision. And you might not notice the wire getting hot, but if you have a thin wire that you pass a lot of current through, you'll notice it getting hot. And that's how, those old element heaters, electric heaters that had the coiled up wire around the ceramic bar.
Yes.
And they glowed red hot. That's just high resistance wire. So that's wire that has very high resistance. And when you pass a lot of current through it, it just heats up so much that it glows. That's how normal conductivity at room temperature works. But if you then take certain metals that can facilitate superconductivity and you cool them down to just above absolute zero. So absolute zero is minus 273. They lose all their electrical resistance and they become what we call a superconductor. Now, we should probably talk about what is the meaning of absolute zero. As I said earlier, heat, if an object is warm, how that's expressed at the subatomic level is that the particles it's made from are vibrating or moving around, right? And yeah. the faster they're moving around, the more they're vibrating, the hotter the object is, right? So as you start cooling down an object, the amount of movement in the particles starts to reduce. They're moving less and less and less. And when you get to absolute zero...
I have a question, just a question.
Yeah.
Is the temperature of the object because they're moving or because it's been heated? Like, is it like, so if they just start moving less, then their temperature is going to fall?
Yeah.
Yeah. So is the movement causing the temperature or is the temperature causing the movement?
So the temperature is the movement.
Okay.
So
That's very profound. The temperature is the movement. Give me a second. The temperature is the movement. Gotcha. Right. Okay.
just like the particle is the wave, Joe.
No, but
just go with it, would you?
No, but the way I was hearing it there, maybe I was hearing it wrong, but it sounded like that you were taking heat away from this thing to cool it down. Whereas I was thinking if it was just left on its own, it would cool down to a certain level.
Well, it would cool down to whatever the ambient temperature in the environment is. But I mean, if you bring the hot thing in contact with something that's colder than it, the heat will move from the hot thing into the cold thing to try and equalize the temperature between the two substances.
Now I understand. Thanks for that. I never understood how food cooked before. Okay.
The concept of absolute zero. You reach a point where, you've cooled it down, the motion of the particles has gotten less and less, and then suddenly you reach a point, minus 273 centigrade, where the motion has stopped. There's no more motion in the subatomic particles. It's called a ground state, and you can't actually measure any change if you try and cool it any less than that. There's nothing you can measure that will tell you you've cooled it further than that amount.
So that's the absolute coldest we can get anywhere in the universe.
Yeah. So how does this superconductivity actually work? And the interesting thing, say you take a wire that you've cooled down to that super cold temperature.
Which they've done.
It's done regularly. In fact, you have probably used machines that have done it, or not you directly, but you've benefited from machines that use it. If you connect that superconducting wire to a battery briefly, and then you disconnect it away from the battery and just leave it in a loop, the electricity will just keep going round and round and round forever. There's literally forever, because it has no resistance. So there's nothing there to use up that energy that's causing the electricity to flow. So it just keeps going.
Right.
It's a pretty mind-boggling prospect. How does it work at the subatomic level? Right.
That was my next question. I had it written down here. How does it work at the subatomic level? Just cross that off.
Cooper pairs. A scientist called Leon Cooper in 1957 in the US theorized that this behavior would happen, and in recent years we've proved him right. The electrons at those super cold temperatures pair up into what's called Cooper pairs, right? And that allows them to carry the electricity. That and a principle called synchronization of quantum waves allows them.
That old principle. I was wondering when you're going to pull that one out.
Allows them to carry the electricity in without any resistance, right? We'll talk about the Cooper pairs first, and then we'll come to quantum waves.
Okay, let's do that.
We've now reached a state where the normally vibrating atoms in the material are no longer vibrating because we're down at almost absolute zero, right? Mm-hmm. So you've got an electron that's trying to carry this electricity through the wire, and it's passing through this lattice of other atoms, molecules that the material is made of. And as its negative charge is making a small little dimple in the lattice as it's passing through. So that's actually slightly concentrating the positive charge of the protons in the lattice by bringing them a little bit closer than they might otherwise be to each other. So there's now this blip of positive, and that pulls in a second electron because the electrons are negative. So that's if you like, the wake, if you think of it like a boat, the wake of the boat, the first electron, is causing an attractive force to the second electron to pull it in. So the electrons pair up as a result of that. Why doesn't that happen at normal temperatures? Because it's a really subtle amount of force involved, and the normal vibration of the atoms, because they're hot, just drowns out that effect. And
right.
So it can only happen when it's really, really cold. So that's the Cooper pairs. Right. Quantum waves. By now, if you've been listening to any of the things I've been saying about physics for the last couple of years.
No, I haven't.
You know that a lot of the particles are both a wave and a particle in physics.
At the same time.
At the same time. And that wave is a quantum wave, right? So what it really means is it's not our conventional kind of intuitive understanding of a wave, like a wave in the sea, for example.
Oh, good.
It's a probability wave. So it means that the location of the particle is a kind of a fuzzy ball or cloud. It's not that the particle has a specific location. And mathematically, you can calculate the probability of exactly where the particle is in various points in that cloud, right? And if you were to do a cross section of the cloud and calculate the probability of where the particle is in that cross-section across the full width of the cloud, you'd find some places had higher probability and some places have lower probability. And if you draw a line, it's a wave. So the peaks are the places where the particle is more likely to be, and the troughs are the places where the particle is less likely to be. So it's not a conventional wave that we think of, but it's a probability wave of somewhere in that fuzzy ball of mush is that particle. I can see the...
Ow. Ow. That's all I'm got. My head is hurting now.
The overload light on your forehead is flashing.
That's enough now.
Now I don't pretend to understand this. I'm only regurgitating what we're told by the scientists.
I think the scientists are wrong. I think there's an exact point and they just haven't found it yet. All of this probability wave nonsense.
So why did we mention quantum waves and Cooper pairs? Normally, in matter that's at normal room temperature, there's billions and billions of tiny little quantum waves all going in different directions and random directions, right? And they're so small, we have no scientific instruments that can observe them directly, right?
Okay, so they're theoretical.
They're tiny, and there's a huge number of them all going in different directions. The Cooper pairs in a supercooled superconductor, their quantum waves, they've all got the same amount of energy, so they start to merge and synchronize with each other. They're so close to each other in identity, for want of a better, that they actually almost become the one thing. So you get this, instead of millions, billions of tiny waves all in different directions, you get this synchronized wave that spans across the full width of the material, and all the Cooper pairs are participating in this one synchronized, like a Mexican wave in a football stadium.
Now I understand. Why don't you just call it a quantum Mexican wave?
Yeah. And that allows the superconductivity to occur. It allows the electricity to travel through the material with no resistance. Got some really interesting applications. First of all, levitation. So
that is an interesting application. If you're going to go straight for the levitation, if you're going to have an interesting application, I think that's the one I would want.
A superconductor, it expels any internal magnetic field out into its exterior, right? If you have a superconductor sitting on the table and you get a magnet, an ordinary magnet, and you just let it go above the superconductor, it will levitate in an inch or two in the air above the superconductor, because it's sitting on a cushion of magnetivity. The magnetism.
There you go. There's a new word for today. Magnetivity.
The magnetism can't get into the superconductor, so it's forming like a cushion between the superconductor and the magnet. It's weird. MRI machines, they need extremely powerful magnetic fields in order to do weird things to the tissues in your body to make them facilitate.
I mean,
the
they're not
imaging.
just taking a photograph. Is that what? I thought they were just taking a photograph.
And they actually use coils of superconducting wire to create extremely strong magnetic fields,
which is cool to minus 200 and diddly.
Yeah, and it's inches away from your body. So the temperature difference between your body and this thing that's a few inches away inside in the middle of the machine is like nearly 300 degrees, over the space of a few inches.
That's astounding, isn't it?
It's incredible, yeah, incredible. Maglev trains, some I think these are kind of experimental in some Asian countries, where the train is literally floating an inch above the tracks, and again they're using superconductor magnetic coils to generate the magnetic fields to float the train, and there's no friction then. Like you could lean on the train and it would move. So
I mean, that's not the best thing. I can see some problems, some flaws with this.
We spoke about fusion reactors a few episodes ago, and
we did.
The plasma there needs extremely strong magnets to steer it around in a circle, and again they're using superconducting coils to do it. So yeah, there's all kinds of applications that are really interesting.
But how do you get the temperature to drop? Like in the machine, an MRI machine, sitting in a hospital room that is ambient temperature.
Yet another fantastic segue, Joe, because we are about to move on to superfluids.
Now, you know what? The best thing about a fantastic segue is if nobody points it out. Oh. If nobody points it out, then it just flows.
I shall
into
try
the
and
next
remember.
thing.
I shall try and remember that.
Thank you.
We're going to move on to superfluids, and there's a superfluid known as helium-4, which is one of the best coolants. What?
Quinoa.
Superfluid.
Oh, right. Okay.
And for a long time, I used to pronounce it quinoa.
Yeah.
until I had to be educated by
The
one of my daughters.
The original Belgian.
So yeah, the superfluids, helium-4 is generally what's used to cool these superconductor coils down because it's really, really good at conducting away heat.
Right.
So what is a superfluid? It's a very similar.
Guinness.
That's the dark superfluid. We're
Right.
talking.
Superfluid.
Let's not cross to the dark side yet.
Okay.
It's a bit early in
Just
the day.
looking for sponsorship again, that's all.
Helium, obviously, to our experience, is a gas. You can get your helium balloons that'll float away on you if you let them
Make
go.
funny voices.
Yeah. But if you, like a lot of gases, if you cool it down, it becomes a liquid. But the interesting thing about helium is you can't make it a solid. It just becomes a very cold liquid.
That is an interesting thing about helium. I didn't know that you just keep cooling it and stays as a liquid.
Now, I think maybe if you also apply extreme amounts of pressure to it, for example, hydrogen, which is very close to helium on the periodic table, they believe in the center of Jupiter, because of the extreme pressure that's involved there, that hydrogen is metallic. So it's quite possible the helium would become a metal if you both made it cold and subjected it to huge amounts of pressure.
Right.
Anyway.
But without the pressure.
Without the pressure, it's just a liquid. What happens, right? It loses all its viscosity. So viscosity is like resistance to flow, or how thick it is.
Mm-hmm. So honey is really viscous.
Honey is really viscous. Water is not very
so much
viscous. But superfluid helium, no viscosity.
Zero.
Right? Zero. One really funny effect, if you put some of it into a cup or any little container like a cup, it'll start to creep up the sides, over the top and around the outside, and dribble away on you. It'll run away, basically.
And freeze the cup, I would imagine.
Possibly. But the thing is, right, because there is no viscosity, even the tiniest amount of force is enough to get it moving. So at the subatomic level, the material the cup is made out of exerts a small amount of attractive force, normally not enough to attract anything, but it is enough to get the flow of the superfluid moving, and it starts flowing up the sides of the cup, defying gravity. Another interesting effect, if you store your cup of superfluid with a spoon and take out the spoon, it'll keep spinning forever.
Now, I assume there are other reasons to cool helium to minus 272 degrees other than doing the magic cup trick.
Well, obviously, we'd like our MRI machines to work.
So it's in there.
Yeah, that's what's doing it. The Large Hadron Collider needs it. The maglev trains need it.
Okay. So anything that has the cooled superconductors needs
generally
this liquid.
they're using superfluid helium to do the cooling. Yeah, it's the most efficient way of getting something down to this. Your fridge freezer is only going to work down to a certain level. You know,
how do they transport? Like, it must cool everything down. It touches
a lot of insulation, I would think.
Yeah.
But it's also a fundamental research tool because it causes this quantum wave. It's the same kind of thing as what was going on with the Cooper pairs, in that you get the particles, their quantum wave becomes synchronized because they've all been reduced to the ground state, to the lowest energy state they can have. Yep. So they kind of start acting as one huge wave across the full width of the material, instead of like a load of billions of individual little waves. And that's kind of what allows this viscosity to be eliminated. It's a fundamental research tool because it allows, normally the effects of those quantum waves are so small that they can't be observed with scientific instruments. But now you got a superfluid, you can observe, if you're doing experiments on quantum waves, you can observe.
You can see them
with the instruments you have. You can see them. Yeah. So
it's kind of magic.
It is kind of magic, and those are the least weird of the weird things we want to discuss. And I think
we're in the entrance gates to the theme park of weirdness.
Yeah, next week is going to be like major weirdness squared. In fact,
look, when you're starting from a point where things are waves and particles, unless they're measured, and then they're particles, and if they're not measured, then they're waves. I mean, you're already kind of weird is kind of in the rear view mirror, and we're driving somewhere completely new.
Weird. You're well into the twilight zone.
Yes.
But yeah, look, that's probably a good place to stop for this week.
Okay.
Because the next topic is something called Bose-Einstein condensates.
Right. Okay. Good. Let's just we'll leave it with the condensates. So I think that's enough with the science for this week.
Yes, indeed. It's been a fascinating discussion about the exotic state one can reach on a Sunday morning. Anyway, see you all next week.
Thanks very much. My head is full. Thanks for listening.